A supermassive black hole can spend millions of years firing two enormous jets across its galaxy. Those jets can travel for hundreds of thousands of light years, inflate giant bubbles of relativistic particles, and transform the gas surrounding the galaxy. Then the central engine shuts down. No new material enters the jets, no fresh particles reach the lobes, and one of the largest structures in the universe begins to die. Astronomers once imagined that these abandoned radio lobes might remain visible for a long time, slowly fading like cosmic fossils. But a new study suggests that many disappear much faster than expected. Using several of the world's most sensitive radio telescopes, researchers identified 12 genuine remnant radio galaxies and found that some of their enormous lobes may spend only a few % of their lives in the dying phase before becoming almost impossible to detect. The result changes an important question about active galaxies. If dead radio lobes vanish quickly, then the small number astronomers observed does not necessarily mean supermassive black holes rarely switch their jets off. Instead, the evidence may simply disappear before we have much chance to catch it. At the center of most large galaxies sits a supermassive black hole. When enough gas falls toward one of these objects, it forms a hot accretion flow and can turn the galactic nucleus into an active galactic nucleus, or AGN. In some systems, magnetic fields near the black hole launch narrow jets containing particles traveling at relativistic speeds. The jets themselves can be tiny near the black hole, but they do not stay that way. As they push outward, they can extend far beyond the visible galaxy. At their ends, the jets deposit energy into enormous regions called radio lobes. Electrons spiraling through magnetic fields inside those lobes emit synchrotron radiation, making the structures glow strongly at radio wavelengths. Some radio galaxies become spectacularly large. Their lobes can dwarf the galaxy that created them. For millions of years, the central black hole continuously supplies energetic particles, replacing the energy that the existing electrons lose. Then accretion changes. The black hole does not need to disappear. It simply stops producing powerful jets. From that moment, the lobes become remnants. There is still plenty of energy inside them, so they do not vanish immediately. But without fresh particles, the existing electrons continue losing energy through synchrotron radiation and through interactions with photons filling the universe. The radio spectrum begins changing in a predictable way. High-energy electrons fade first, causing the emission to become progressively steeper at higher frequencies. This spectral aging works almost like a clock. The problem is that dying radio galaxies are difficult to find precisely because they are dying. Bright, active radio galaxies are easy to detect. Their cores may still shine, jets remain visible, and hot spots at the ends of the lobes reveal where fresh particles are being injected. A remnant may have none of those features. Its central core becomes weak or invisible, its hot spots disappear, and its diffuse lobes fade into the background. Previous surveys therefore risked finding only the most obvious, long-lived remnants, while missing a much larger population that faded rapidly. The new study attempted to look deeper. Researchers examined 14 candidate remnant radio galaxies in the XMM-Newton large-scale structure field. They combined data from the Meerkat-MICTI survey in South Africa with observations from the upgraded giant microwave radio telescope in India. They then added measurements from LOFAR, the GMRT, and the Carl G. Jansky Very Large Array, giving them continuous information across radio frequencies from roughly 144 MHz to 1.5 GHz. That wide frequency range was crucial. Looking at a radio galaxy at only one or two frequencies is somewhat like trying to estimate a person's age from two photographs. The broad spectral coverage allowed researchers to see how the emission curved and steepened, providing much stronger evidence about the age of the electrons. The first surprise was that not every apparent corpse was actually dead. Of the 14 candidates, 2 showed evidence that their central engines were still active. Only 12 survived the full multi-frequency test as genuine remnant radio galaxies. That alone demonstrates how difficult these systems are to classify. A faint core or a weak jet can easily disappear in limited observations and make an active galaxy look dead. Then researchers measured the ages of the confirmed remnants. The total spectral ages ranged from about 8 million to 42 million years, with a median of only around 12 million years. That is younger than many of the remnant radio galaxies emphasized in earlier studies. The sample therefore appears to contain a previously underexplored population of young dying radio galaxies. More strikingly, the fraction of each galaxy's radio lifetime spent in the remnant stage varied enormously. In some objects, the dying phase accounted for only about 4% of the estimated total radio lifetime. In others, it represented as much as 83%. Some lobes may remain detectable for a substantial fraction of their existence. Others could fade so quickly that astronomers have only a narrow window in which to observe them. Why? Part of the answer may come from distance. The universe is filled with a cosmic microwave background, a sea of ancient photons left over from the early universe. As we look farther away, we see galaxies at earlier cosmic times, when the energy density of that radiation was higher. Relativistic electrons inside a radio lobe can collide with those photons and transfer energy to them through inverse Compton scattering. More background radiation means faster energy loss. The researchers found a significant relationship between redshift and spectral age. The more distant remnants in their sample tended to appear younger. The interpretation is that radio lobes at higher redshift may lose their energetic electrons more rapidly and therefore fade from radio surveys sooner. This creates a strong observational bias. Imagine two identical black holes switching off their jets, one relatively nearby and another billions of light years farther away. The distant lobes may pass through their detectable remnant phase much more rapidly. By the time astronomers perform a survey, they could already have faded below the instrument's sensitivity. The universe might therefore contain huge populations of dead radio galaxies that have become nearly invisible. And those invisible remnants matter because jets influence their surroundings long after leaving the immediate neighborhood of a black hole. Powerful AGN jets can heat gas, inflate cavities, and redistribute energy through galaxy groups and clusters. This process is one of the mechanisms astronomers invoke to explain why some massive galaxies stop forming stars. Gas needs to cool before it can collapse into new stars. Inject enough energy into that gas and star formation can be suppressed. Knowing how long jets remain active, how frequently they restart, and how long their remnants persist is therefore essential for understanding the life cycles of galaxies. The new observations also revealed that radio lobes do not simply freeze when the jets stop. Spatially resolved age maps showed systematic differences across some extended remnants. Different parts of a lobe contained electron populations with different spectral ages, consistent with plasma continuing to move after the central engine switched off. The black hole may be silent, but the structure it created remains dynamic. Old plasma can expand, compress, or interact with the surrounding environment. In compact remnants, the researchers found more irregular patterns, suggesting that local conditions and magnetic structures can strongly affect how the lobes age. This creates an important distinction between a dead engine and a dead radio galaxy. The central black hole can stop feeding the jets relatively suddenly. The lobes, however, then enter an extended afterlife governed by plasma physics, and sometimes the black hole may turn back on. Astronomers already know of restarted radio galaxies where new jets appear inside older fossil lobes. Some systems even contain multiple pairs of radio structures created during separate episodes of activity. That means black hole jets may behave less like a machine that switches on once and eventually dies, and more like a geological geyser that undergoes repeated active and quiet cycles. Measuring remnant lifetimes helps determine those duty cycles. Suppose astronomers survey 1,000 radio galaxies and find only a small number of remnants. One interpretation would be that the active phase lasts enormously longer than the inactive phase. But if remnants quickly become undetectable, the observed ratio tells us less about how often black holes shut down than we previously thought. Future SKA surveys will combine enormous sensitivity with the ability to detect low surface brightness radio emission across large areas of sky. They should uncover faint remnants that current instruments miss, especially at higher redshifts. The new study offers a preview of what that population could look like. Astronomers could then reconstruct the activity history of supermassive black holes across cosmic time. Do black holes behave differently when the universe is young, and how much energy do their jets inject into galaxies between each active episode? The 12 remnants in this study cannot answer all of those questions. The sample is still small, and spectral ages depend on assumptions about magnetic fields and how particles evolve inside the lobes. The researchers are not claiming that every dead radio galaxy disappears after 12 million years. What they have found is evidence for a younger, faster fading population that earlier surveys were probably biased against detecting that changes the picture. For millions of years, a supermassive black hole can create one of the largest structures associated with any single object in the universe. Its jets carry energy far outside the galaxy. Its lobes expand across intergalactic space, then the engine shuts off. The enormous structure does not collapse dramatically. There is no explosion marking the end. Its electrons simply lose energy. The radio glow becomes steeper, fainter, and harder to distinguish from the background, until eventually one of the most powerful episodes in a galaxy's history becomes almost invisible. The new observations suggest that this disappearance can happen surprisingly quickly. The universe may therefore contain countless ghost structures left behind by black holes we would classify today as quiet. We cannot see most of them anymore. But for a brief period after the jets die, radio telescopes can still catch their fading echoes and reconstruct what the black hole was doing millions of years before.